like to invite now for the second QKD Architecture lecture, again, Professor Kanellos. Please be a bit...
Short. All right, thanks, Elias. I'll try to be short, but sharp. There is a challenge in the talk because of the type of the audience that is not homogeneous. But I think that we will try to address something that already from Hannes' presentation was identified as a key technology in order to develop the quantum key distribution technology into quantum networks in the large scale. And this is, of course, the need for an intermediate layer that abstracts the key information and is able to manage this, the one called key management layer. Now, to make myself clear, we will start with reviewing the key management basics, what was the need and the motivation for this. We will have a brief look at the standards and best practices. This is to briefly educate ourselves on how these systems look like. And then I will attempt to show and discuss briefly how we managed to deploy this within the Hellas QCI as a practice that not only takes advantage of the current state of the art, but also tries to apply some useful extensions. And I will conclude my talk with a hidden slide. Now, thanks to the description of Yannis Giannoulis on what a QKD technology is, we can easily identify that we have a link, a point-to-point link. So we normally use an Alice and a Bob. They exchange photons. They do implement the BB84 protocol. At the very end, we manage to exchange a series of bits or two or keys, if you like, that are holding the fundamental principle of being, at least in theory, information theoretic secure. And this is very, very, very important. This is why QKD has been put in the spotlight in the first place. However, this is just a point-to-point link, right? So we need to see what are the options for extending it into a network. Now, as it became obvious from Yannis' talk, we have a sensitivity to the attenuation and therefore a limit on the reach of such point-to-point links. Typically, they come with a maximum of 30 dB. The commercial systems today, they can go around 30, 33 dB. So with a typical fiber attenuation of 0.2 dB per kilometer, we can go easily calculate that we can not exceed the 150 kilometer range. So one way to address this is through hardware development, employing quantum repeaters, or all these very, very difficult scientific approaches that are proposed. Or another way to abstract our network, try to maintain the security at the information theoretic level that we managed to gain through the QKD technology and proceed as such. And the way to do it is using the key relay mechanism. So what is this? You have a pair of QKD devices, an Alice and a Bob, that produce symmetric keys between Alice and Bob. And then you have to use a second pair, again, a second Alice and a second Bob that create a similar pair. Now, in the node in between, where you have the Bob from the first system and the Alice from the second pair, what you can do is actually apply what is called a one-time pad encryption. That is, again, an information theoretic secure process. So this is practically XORing each bit of the first of the keys of the first QKD link with each bit of the keys of the second QKD link. We call this a relay mechanism, and it is important because, at least in theory and in principle, it maintains the information theoretic secure process that we gain with QKD. However, that comes with an additional constraint that the intermediate node is now a trusted node. So we have additional requirements on the security, on the physical security of these nodes that need to take place. Moreover, we can use a variety of key resources to use in the key protection, and I'll come back to that in a minute. So this was just to extend the reach. So from 150 kilometer max, we could go to 300, and by repeating this linear process, we could exceed to 450, etc. In order to build a network, we now understand that we need to abstract this process in what is called a key management layer, in which layer, the abstraction of the handling of the keys will allow us to monitor the processes, distribute the process of exchanging the keys, and do all sorts of processes that improve the performance of the key handling. Now, this has started already with an example on the right side of my slide, which is the Tokyo network back in 2011, where they designed and implemented a physical implementation around Tokyo with 6 nodes and implementing a KMS layer. A lot of research has taken place since, and in 2020, that is just 4 years ago, we had eventually a recommendation from the ITU, from the International Telecommunication Standards Office, on how to implement quantum key distribution networks, and in particular, what this sort of key management should look like. And as you see, the fundamental principle is that you have a quantum layer where the physical appliances are taking place and physical exchange of qubits is taking place. The keys are pushed up into the key management layer that abstracts the keys and is able to buffer and store the keys and process the keys. And you need a QKD controller that controls this key management layer, and of course the application layer where these keys are pushed. Now, while in principle this sounds relatively simple, the implementation of such a network, the complexity of the implementation of such a network is again on the right side, where you can see all the different blocks that need to take place in order to implement such a network. Now, if I attempted to go in each of these blocks, each block is important, but it would take me a day to analyze the key management. I will only take the opportunity to briefly look into these software boxes, all right, and block diagrams, and see, just get a familiarization of what the key management is all about. It comes with 2 layers. The lower layer, the key management agent, that talks to the QKD module, so you need an interface to fetch the keys from the QKD module. I'll come back to that in a minute. Store the keys, be able to do the process that we discussed already in relaying the keys with the neighboring nodes, and of course perform some functionality along the life cycle management. On the upper layer, you need what is called the key supply agent, the KSA, that is now an agent that talks to the application layer and actually collects the requirements, the needs for this sort of keys, and is able to coordinate with the KMA in order to push the final key products up to the application layer. We have, as I previously mentioned, a few schemes on the key relay. The first one is, suppose the simplest case, this is the linear case where you have QKD appliances, one next to the other. So we have a QKD box analysis in node A and another QKD box in node B. So they exchange the same key, say key AB. So the first option is to do the point-to-point relay in a way that we use the second pair to encrypt the first, the keys that were produced from the first pair. And in this way, propagate in sequence the key of the first pair all the way to the receiver end. So you see that eventually we conclude with the key AB to the KMD, to the last node. Another option is to use an engine, a random number generator or an arbitrary number sequence that we want to encrypt. So we use the key AB to encrypt this random number, and in sequence we propagate this to the second node. We have to XOR, and by XORing key AB with key AB and the random number, then we can get through the fundamental principle of XORing, again the random number. And in this way, we can propagate all the random number key all the way to the end node. Now, these two solutions are equivalent. It's rather a choice of implementation rather than security aspects. But the common ground is that the key, the cryptographic key, is revealed in all the trusted nodes along the line. Okay, so you can notice that key AB is exposed in every node here. Key Rn is exposed in every intermediate node here. And that may create some security issues. The third approach is the centralized KMA. In this case, we do not perform the XOR or the revealing of the key that we want to propagate in every intermediate node. We perform XORs along two neighboring nodes, and we transmit the result into a centralized management system. All the XORs are performed at that centralized node. The solution is again equivalent, but the implications on the security of such solution using a centralized node are still to be investigated. However, it is out in the literature, it is a valid solution, and we all need to look at it. Now, in favor of time, I'm not going to go through the details of the various standards. I'm only going to state that there is a European standard in place that refers to the key delivery. So this is the protocol, if you like, the communication process that takes place between the QKD equipment and the key management or any other consumer on how to fetch the keys in a secure way. And this is using HTTPS protocol. The good part is that this has become a standard across most vendors, and that allows for compliance with most of the KMS and the consumers anymore when trying to fetch QKD keys. There are another pair of standards that are very important for reasons that were mentioned by Hannes and other speakers previously on the need to deploy the networks in a software-defined fashion. And the reason is that as software-defined networking comes with some advantages in classical networks, and this is the ability to monitor the network performance in real time and dynamically change and optimize the performance of that network, SDN in QKD should be able to do the same. So ETSI QKD GS15 is a protocol that was actually released maybe less than 2 years ago, or about 2 years ago, and was attempting to specify how the SDN agent of each particular node should operate. And this comes in link with ETSI QKDGS 18 that aim to describe how to orchestrate such a network that is populated with SDN QKD agents or nodes with a capability of SDN QKD. The benefits for doing so, and I'm going to stay to that, is that we can then provision an end-to-end QKD network. So that means that I can describe what my service should look like and optimize the path, optimize the different performance metrics of my QKD network. Now, these are very important aspects, but have not been realized in full. We are just starting to see deployments on these networks. When it comes to the HELAS QCI, we try to capture all of that. And in fact, we followed the three-layer architecture with the quantum layer, the KMS layer, and the application layer, and we put some requirement in each layer. For example, in the application layer, we define that we want to support layer 1, layer 2, and layer 3 encryption, i.e. Encryption at the OTN layer, encryption with MACsec, and encryption with IPsec. OTN-sec actually allows an encapsulation of all layers and comes with some additional benefits that my colleagues will discuss tomorrow in more detail. However, we also wanted to make sure that we have a backward compatibility, and this has come clear as the QKD technology is new and people are not ready to sacrifice any operation on something that has not been tested yet. So this is absolutely necessary. Also, the ability to support the integration with other technologies such as PQC. And we see that not only in the hybridization of the keys fed using QKDs and PQC keys in a blended fashion, but also hybridization of the KMS layer, for example, in the authentication of the nodes, of the KMS nodes, processes, etc. Now, on the KMS layer, things are clear. We discussed them already. There are these standards, so all we needed was to make sure that we have the technologies that comply with these standards. And eventually, on the QKD layer, we focused on supporting DVQKD, no particular reason for that, just it was more mature at the time. We also wanted to support switched QKD, is a concept that we don't have the time to analyze, but we think it's really useful. Now, hopefully, we bounced on a technology platform that came from Nokia. So they had the security management system, what they call the SMS, that was already implementing some classical, some symmetric encryption with classical keys. And this is a feature that really fits the QKD. And in fact, they had already standardized and certified this with NATO certifications. They recently extended their technology in order to be able to match or to retrieve QKD keys in the process. And this is where we jumped in and we said, all right, this seems to provide us a backward compatibility, because if everything goes wrong, then we switch to classical certified operation. But in the meanwhile, while we have QKD networks that operate and are able to push keys into our encryptors, then everything should look fine, and we could proceed with sort of certified encryption processes with QKD keys anymore. They suggested, or they had implemented their encryption services with Evolution Q systems as the mediation layer. Evolution Q is a company that was able to comply with what ETSI 15 and ETSI 18 describe on the ability to manage key requests and adjust key consumption and key buffers in the relevant nodes. And therefore, we think that this already complied with our requirements. So we put everything into test already since February, and we managed to demonstrate this hybrid operation, so encrypting in the various nodes with QKD keys or classical keys if the QKD or the KMS fail, and we managed to test the coordination of the application layer with the KMS and the QKD. And of course, not to mention that this was a critical part as well. In all other implementations that we had seen so far, a QKD link was deployed in every classical link. So there was a QKD link in parallel. This was, to our knowledge, one of the first implementations where we actually managed to provide 3 separate links with only 2 QKD links. And in this way, demonstrating all the features of the advanced KMS, because this is where it became quite demanding in relaying the keys and balancing the keys and buffering the keys, but also in demonstrating this resource usage optimization. More on that you will see with my colleagues tomorrow. We have deployed this POC, in fact an advanced version of it with 2 pairs of thin quantum equipment and 2 pairs of ID quantic equipment, and you should be able to experience this in more details. So in the summary, we've been pursuing this quest for building a pan-European QKD network that stems from the EuroQCI requirements. LSQCI is complying with the international QKD standards, and in fact it is extending them in a sense that we deploy hybrid encryption with QKD and classical keys. We are able to already put in place a form of orchestration of the application layer with the key management and the relevant QKD layer, and of course we have already implemented a successful validation of this setup with the POC. Now, the bonus slide to conclude is the fact that I could not resist not referring to our activities with respect to the quantum internet. So I think that the topic was covered fairly well through previous speakers. The idea is that instead of implementing a specific application that is QKD, what we do is actually allow the communication, the generic purpose communication between 2 nodes to exchange qubits. So the challenge here is in fact not to collapse the quantum state as it is transferred from one node to another. And therefore, in the intermediate nodes, you need this sort of repeaters that has already been discussed and presented by Andrea in implementing the BSM, the Bell state measurements. Just to answer a question that was put online, no, the repeaters do not affect the quantum state. This is in fact the definition of the quantum repeater. The way that they do it is much more complex. It relies on the performance of the BSM that is actually transferring or identifying the correlation between the quantum states of the 2 entangled pairs that are arriving in the BSM, rather than reading or in somehow defining the quantum states of either states. And this is how we manage to maintain the quantum state without affecting it. Now, back to our discussion and where we stand with the quantum internet. Obviously, we need entanglement distribution, so that means that we need entanglement pairs for photon sources. So we are acquiring 2 entangled photon sources, and we are also acquiring 16 single photon detectors. In fact, this procurement has recently concluded. They are coming from single quantum, and the idea is to be able to implement state-of-the-art active entanglement distribution and hopefully quantum teleportation in Greece in the near future. All right, thank you everyone.